Hey, greetings, Chem 110H. Dr. Bevilacqua here. I'm going to go over Quiz 5 briefly and just talk about some of the major points that our graders brought up about some of the points to improve on for this quiz. And so let me start with question number 1. And one of the things that I want to point out here is that some of you guys seem to struggle drawing the DMCH, the dimethyl hexane, and so you want to make sure that for methyl you put in CH3 and not CH2OH, which is basically a methanol substituent, just methyl CH3. Most of you did a good job identifying the IMFs correctly down here. So good job on that. Um, but the thing that caused the greatest amount of trouble was identifying which was more soluble. And there was a misconception that this 4-methyl cyclohexane methanol um, would be less soluble when in fact it's more soluble. And you can see down here that it's more soluble. You can see the right answer. And one of the misconceptions here that led to thinking that it would be less soluble was that some of you thought that water would not be able to break up the stronger IMFs. You got the IMFs being stronger, but then thought that water couldn't break them up because these were stronger here. And so, uh, so on the one hand, it is harder to break the interactions up between the MCHM molecules than it is between the DMCH molecules. But you also have to remember that you have to break apart the water molecules in both cases. And here you can make strong bonds between this OH and hydrogen bond with water, whereas here you cannot. And so even though you have to break strong here and break strong in water, not shown, you get to make strong and strong. And so it's kind of thermoneutral. And of course, what drives it is the gain in entropy from having more positions of everything, more positional disorder, more randomness. Whereas over here, this is easier to break, but you can't form any bonds with the water. And so it's unfavorable because you're breaking up water and not restoring it with strong bonds. Okay, so that's how you want to think about that. Yeah, one other misconception that was pointed out is that some of you wrote that hydrogen bonding causes dipole-dipole, or dipole-dipole causes hydrogen bonding. But they're both the presence of the electronegative atoms. So there's a delta minus on that O, delta plus on that H, and it is the very same thing that also gives rise to hydrogen bonding. You get the charge separation of the minus and the plus. So whenever you write down hydrogen bonding, you must also write down dipole-dipole. Although the converse doesn't have to be true. You can have dipole-dipole without hydrogen bonding, for example, in chloroform. Okay, so let's continue on here. Get to question 2. So you guys generally did very well on this question, and almost everybody drew the curves correctly. So good job. And meaning that you drew this liquid gas line as a curve, as you should, because that's the vapor pressure curve. And as you know, as you increase temperature, the pressure goes up exponentially because you create more molecules of gas and that go from the liquid into the vapor. Same thing is true here. Let me just grab the pen and emphasize that this particular line right here should be curved, like kind of like that. Okay, and continuing on. Yeah. Some of you lost a point or two for not drawing the liquid or gas meniscus that the problem asks for. And so if we look at this, it says that you should draw the contents inside the apparatus at the molecular level in all 5 relevant points, and identify the triple point. So you want to just go ahead and pay attention to where the meniscus is, and this is a substance that's less dense in the liquid. Sorry, in which the solid is less dense than the liquid. So you should have a meniscus right here. Sorry, right there, and you should also have a meniscus right here. Okay, because those points, one is right there on the liquid gas line, and this one's right here at the triple point. And then the last thing is your drawing should show that the solid should float on the liquid. Okay, so actually there appears to be a typo in the answer key, in the sense that the solid, it should look like this. Here's the piston in the chamber, and the solid should be up here. And then we should have the, I'm sorry, let me go back and redo that. We should have the vapor, and then we should have the liquid, and then we should have the solid kind of floating up above, like so. And then what's left is a little bit of space right there, where the liquid's going to be. Okay, let me draw that one more time for you, a little bit bigger. Okay, triple point, vapor, liquid, meniscus, and the solid floating, some ice cubes, like that. Okay, that's how that should look. That should go over here with the triple point. Okay. Going on to question 3. This was the question that caused you guys to lose the most points. And some of you struggled with properly drawing the molecules and put extra hydrogens and methyl groups on. And a lot of people didn't understand what would cause CHBr3 to be more soluble in water than the CHI3. And some of you wrote that CHI3, this guy right here, would in fact be more soluble. And you reasoned that that would be true because it's bigger and has more London dispersion forces. But you ignored the more important differences on the effective polarity, which kind of trumps that, at least. Sorry about that pun there, unintended. That makes the intermolecular forces of the polarity are greater than those from the London dispersion forces, unless they're really huge differences in the size. Okay, and so so some of you correctly identified that CHBr3 would have a greater dipole, but thought it would be harder too for water to dissolve it, because it has stronger IMFs. But remember, you're breaking stronger intermolecular forces in here and in the water, but you can restore that with strong between the water and the CHBr3, and of course you have the entropy to drive that as well. And if you want me to show you here where the dipole is, let me go ahead and do that. So the bromine is more electronegative than the carbon, and so each of these bonds is polar like this, with the negative end near the more electronegative atom, the bromine. And because of the nature of this, and you can sort of think of this molecule almost like a tripod sitting on the three bromines on the floor, then you can add these all together and get a kind of a super dipole that goes in this direction from the sum of all those guys with a delta plus, delta minus, and then you can get IMFs between subsequent CHBr3s, and that leads to stronger IMFs, which then also leads to greater solubility. Okay, let's move on to the last question. And, you know, this question, you guys did a great job. Almost everybody got it correct and used the equation to calculate pressure. Some of you had some small math errors, and so so the other thing is that if you use more sig figs, then the more accurate answer here is actually 853. And this number up here should be 34.35, which will get it a little bit more accurate. But the grader was lenient here because it's so easy to get off in your figures on these particular problems. The best way to do it is to leave all the numbers in your calculator if you can. Okay, so so as long as your calculations were consistent, you should have gotten the credit on that. I hope this was helpful, and let us know if you have additional questions. Thanks for listening. Bye-bye.